Next speaker is going to be Professor Petros Koumoutsakos from Harvard.
Hey, good afternoon, everybody. I'd like to thank Karthik for putting this program together. And I also would like to thank all the speakers and panelists. I have learned a lot. I'd like to give you from the beginning that I am a skeptic and at the same time an enthusiast of artificial intelligence and its interaction with computational science. And I would like to give you where I am enthusiastic and where perhaps I am more skeptical, and I leave it to you to judge what is right and what is wrong. So we are interested in solving problems, and here is a representation of perhaps of how you can classify problems of the world. You can have problems for which you have first principles, and then you can have problems for which there is an abundance of data. So if you like, engineering and physics, which have equations like the Navier-Stokes, so I would put it in this category. And then there are other fields like medicine, social science, and finance that are more data-rich. And of course, there's other places where there is no data and no principles, and that's where you find lawyers and experts and other people. And of course, what we are interested in engineering is to try to drive ourselves towards to the side of data. Karthik told me, please be provocative. Normally, I am not, but because of Karthik. So how do you solve hard problems? So here is an answer. How do you solve hard problems? You use lots of training data. And then what you do is you do a big, deep neural network. And then, of course, success is the only possible outcome. Right? This is according to the founder of OpenAI, Ilya Sutskever, who made this statement in 2015. And in Greek, we have a word, it's called hybris. And that's a hybris of those times. Nevertheless, that's where the enthusiasm comes. There is these foundational models. And what are these foundational models? There is this AI neural networks trained on massively unlabeled data sets and can do a lot of different things. And you saw this slide already. It's from this famous Stanford paper, and I would like for those of you to spare you some time so you don't have to read the paper. There's two things you have to learn. One is emergence, the other is homogenization. What is emergence? Emergence is if you have a ML, the how is performed, and how a task is performed emerges from examples. So here's emergence here. Also, with deep learning, high-level features are also emerging. And with foundational models, advanced functionalities, such as in context learning, is also emerging. And now there's the homogenization, which is basically that you can do something and you can transfer it across different fields. And I think this is wonderful, and this is interesting, and I would like to argue this is not new. And I would like, before to tell you that it's not new, I'd like to tell you another way of thinking about solving problems. And it's my favorite book. It's called the book of Judea Pearl. It's called Causality. So I have adapted something from that book. So we are seeking knowledge, and then what we do is we are making assumptions. Out of these assumptions, we create causal models, and then you have testable implications. In creating causal models, I do not exclude data. Now, after this, you can have a query to this knowledge. You can ask a particular thing. You can design something. And then you go and you say, can the query be answered? And then if it's no, you go back, you test your assumptions, your causal model. And if it's yes, then you have an estimate. You have a code. You have something that you can have as a recipe for answering the query. And that's not over yet, because then you have data, and then you can take the data and you can create statistical estimates. You can perform uncertainty quantification of your models, and this is an estimate to answer your query. So this is what we all scientists do all the time. You can juxtapose it with the lightness and flexibility of foundational models. Just throw everything inside and something will come out, versus this, which is more structured, it's more painful. Perhaps there's a way to combine the two. So, talking about fundamental physics and first principles, well, we have emergence. We have emergence in everything we have been doing so far. And I will give you an equation. I will give you some code, and I will give you some great people, because that's what makes the world go round. And then we can produce you things like that, which is a bubbly flow. This is a state-of-the-art simulation simulating tens of thousands of bubbles. It's repeatable. It can also take the code, and you can produce something else. You can produce bubble crystals inside microfluidics. So this is also the ChatGPT version, if you like, about give me a breaking wave with bubbles. This is not repeatable. So I put them the two together just to have fun. Anyway, so we continue. We have fundamental principles, first principles, and then here comes homogenization. So here I'll give you an example of homogenization. There is a method called particle methods. If Robert Krasny is in the audience, he should be excited for what's coming. So we take particles and interactions, and this is a very powerful tool because all you do is you move the particles around, and then you solve Newton's law on the particles. That's all there is there. And if you are careful and you chase the right-hand side as to what is the force field, here is vortex reconnection using 3D vortex methods, and this thing is at the same time, you can take practically the same code, change the right-hand side, and you have molecular dynamics. And if you learn to think and program in these ways, you can have very powerful tools. And that's actually what we have been doing in our lab, that we created software that you can change the right-hand side, and the rest of the things can be quite flexible, so you can do all these different things. You're not doing really different things. You are doing basically this principle of homogenization in practice. That's what we have been doing in scientific computing. So now computing is about joining boundaries, and I would like to show you one more thing. So computing joining boundaries, I was interested in joining the boundaries between fish schooling and blood flow, because I thought this is collective phenomena, and then you can have a certain kind of complexity that you can study. So when you develop all these different things, what is very, very valuable is that you have all these pieces of the puzzle. I can take all these pieces of the puzzle that we had developed in our lab and reconfigure them, and I can try to answer different problems. So the important thing is that you have the core of the things and you have interfaces between the different topics. So when you develop software, you're thinking that this is going to interface other software. So here are some results. This is a state-of-the-art simulation. It involves the equivalent of about 10 trillion grid points. It's a simulation of about 400 hydrodynamic swimmers solving the full Navier-Stokes equations in complex deforming geometries using wavelet adapted grids and doing some very good performance on the LUMI. So here is a simulation of this. We are planning to put learning, as I will come back later. And here is another state-of-the-art simulation of particle methods. This is dissipative particle dynamics. This is separating particles by size through the posts of a microfluidic device. This was a finalist for the Gordon Bell Prize of 2015. And in this case, we did a very large-scale simulation. What you see is not the full-blown simulation. We did a simulation using 1 trillion particles in 2015. This is much less for the purposes of visualization. And we found actually how things can be separated. And here comes the problem about scientific computing. Now, if I take this and I said I have an in silico lab on a chip, the problem was that I found that if the chip geometry changed or if the type of the particles changed, I was not able to predict experimental results that I did not have. And why I could not predict, I was collaborating with people at the time that they gave me results that they said the method has been validated. So you take a red blood cell, you stretch it, you find out the angles, you put a red blood cell through a constriction, you do all these tests, and then you actually, now, because I said something bad, this thing froze. That's exactly what happened. Huh? It doesn't let me go out of full screen. The fastest will be to do what I will do now, which is to turn it on and turn it off. I'm sorry for that.
It came up.
It came up, but not on my screen. I don't know what's going on. It doesn't even turn off.
Let me see here.
Well, there goes. There it was. Okay. Long story short, you'll see a lot of simulations, and a lot of these simulations, there will be experimental data that they have been captured. There will be about 7 cases of experimental data that has been captured. The question to you, is the method validated? How do we validate numerical methods? What does it mean partially validated? Why do you think it's partially validated? So I thought, when I saw 7 experimental results, that they were very diverse and very capturing all sorts of different phenomena. I thought actually that indeed the method has been validated. So if the method has been validated, why does the method not generalize? And the reason for that is, let me not go into all my emails right now. Sorry about that. I hope I get 2 extra minutes. Sure. View, light table. Okay, the reason that the method is not validated is because of this. The method is not correctly validated is because of this. It's people, when they do these complex models, they go and they change their parameters by up to 3, 4, 5 orders of magnitude until they capture a particular experimental result. And that's a big pathology that many people do in scientific computing. Not only in machine learning, people tweak things, but people tweak things also until they get the experimental results. And if you have a model that has about 7 parameters, it's trivial to capture something that propagates linearly. You just have to do it. It better capture it, otherwise it's completely false. So this was the thing, actually, that I saw from in many other places, and that's actually what was one of the motivations to look into data-driven models, because first principles, we really don't have first principles. So now, capabilities of machine learning. Machine learning is fantastic for pattern recognition. So can we use this capability to use it in scientific computing? The first time I did that, I was a postdoc at the Center for Turbulence Research, and I did deep learning by accident. We kept adding layers in a neural network to do reconstruction of a turbulent flow field. And the method of the time was the proper orthogonal decomposition. And we could show that you could take a neural net and have the proper orthogonal decomposition and a nonlinear representation with the same neural net. It took me about 3 years to publish this paper because people were saying, what's the big deal? It's just a nonlinear proper orthogonal decomposition. But of course, people paid more attention. 13 years later, this is the Big Bang moment, where actually Ilya, that I mentioned earlier, he's one of the co-authors of this paper, where they did this classification like nothing has ever happened before. And then we talk about patterns. So patterns, there is success for pattern recognition. Patterns can exist also in dynamics. Can you imagine perhaps that you have the latent space of a dynamical system? Can machine learning recognize them? And here comes a criticism that I mentioned earlier, and the criticism that I mentioned earlier is that time is an ML frontier that, in my opinion, and contrary to others, has not been broken, and there's a lot of corpses to be found there. And I will show you one of them right now. So forecasting on unseen temporal data, you take some data. I will take some data from a PDE that I can solve, and I pretend these are real data, but I know the answer is going to evolve in the future. And then I will try to predict the dynamics on unseen data. My toy problem is the Kuramoto-Shivasinski equation, which actually, be careful when machine learning people present you solutions of the Kuramoto-Shivasinski. The lower the L, the smoother the things it is, the easier it is to simulate it. So you can simulate it with a finite difference method, and you can get data for this. So what you do is you take some of the data. I'll show you how much data I get. And actually, because we were using recurrent neural networks with LSTMs, we had to downsample the data using the SVD components. So what we do is we train on this side. So X is on the horizontal direction, T is in the normal direction, And then I want you to see the RNN, LSTM, how far can it go. So you do the training, and after training, you're doing pretty good. If you keep going, you start to fail. You continue to do well, you start to fail, and then once you start to fail, you can fail dramatically. And actually, whether you fail dramatically or not, this is also very elucidating. If you have a low L, which makes it a very dissipative solution, what you see is that you fail much later than a higher solution, but you more or less stay on the manifold. And in my opinion, machine learning is able to work only if there is a stable manifold and is able actually to capture the manifold. If you have multiple manifolds, extreme events, and etc., I think it becomes very, very tough. Nevertheless, there is this paper where actually our work is cited that we have shown that machine learning has the amazing ability to predict chaos. I could not believe my eyes that we did that. So in any case, we made it to Quora magazine. That counts for something. So there's papers here that explain what's going on. So I think you can look at that. So now, are we dead? I think we are not dead, and there is promise and lessons to be learned. So the lessons to be learned is that, in fact, you can propagate, after all, the dynamics after a certain time. And actually, if you think, we took an old idea by Yanis Kevrekidis, the equation-free method, and by putting in machine learning ideas like encoders and decoders, what we did is we can propagate the dynamics for some time, and then we have metrics of when these dynamics are not accurate. Basically, we use ensembles of recurrent neural nets. Then we have a decoder, and with a decoder, we can go back out to the microdynamics. So we call this learning effective dynamics, where you go in and out to some kind of a latent space, and you try to propagate forward. The idea, as I said, comes from equation-free together with machine learning, and there are several other people working on similar ideas. How good is it? Let's look at it, and I'll show you successes and failures, and something which is also surprising to me. I hope you understand the cycle is quite easy, and of course, you win or lose depending on how much time you spend on the expensive micro versus the non-expensive macro. So let's go back Kuramoto-Sivacinski, and in this case, I will not go back and forth. I will stay only in the latent space, except that this time, instead of doing SVD, I have used a variational autoencoder to go into the latent space. I have actually identified the 8-dimensional manifold of the Kuramoto-Sivacinski. The autoencoder does that. And now if you look point-to-point comparisons, they're not the same. But nevertheless, if you look at the phase space, you see that this method captures the phase space. So these methods are very good at capturing statistics, so I can imagine they can capture also weather and other things if there is some kind of statistics that you capture. But if you care for detail, I'm not so sure that this is the case. Now, the next thing is you do flow past the cylinder, and the usual trick is you don't mention the Reynolds number. The Reynolds number here is 100. And Reynolds number of 100, basically, it's an oscillator. You can solve it with 2 degrees of freedom. So indeed, using a latent space of 2 degrees of freedom here, we're able to do very good predictions. Not only that, we capture the vorticity, but we can also capture the drag of the cylinder, which we didn't look at, within 4%. So the question you should ask any person that shows you Reynolds number of 100 with their method, ask them, how about your method and Reynolds number of 1,000? So this is the question we ask ourselves, and we fail. We fail because we have problems in the root mean square error that perhaps are not very clear to you, but I will show you where the errors are. And the errors are near the surface of the cylinder, and that makes sense because that's where vorticity is produced. And when you use a uniform autoencoder and a decoder, you don't pay attention to the physics. So it's important that you pay attention to the physics when you analyze your data. That's something we are doing now, and this seems to be working better. And I will close this chapter or this section of my talk about how do you take now generative AI and combine it with these ideas. So I'm sure many of you know about this diffusion process. You get some simulation and you diffuse it, and then you can go back and undiffuse it by with reversing the process and learning something about that. there is an interesting component which is guided. Guided diffusion says that you generate data from a conditional distribution through conditional information. And now, what we do here is we use the latent dynamics as a guidance of doing the forward and the reverse diffusion. And the latent dynamics are containing information that is not necessarily inside the microdynamics when you do the diffusion. So this is the story. You go back, and in this time, you go back and you have a guidance. We repeat this with generative learning of effective dynamics, where we have done some kind of training of our diffuser, of your diffusion process. Then we have generated the guided diffusion reverse process through a neural network. Then we evolve the dynamics with a transformer, the latent dynamics with a transformer. And again, whenever we want to recover the microscale, we use the guided diffused models. And now the results actually were, to my surprise, spectacular. It took me 4 months to believe my postdocs that this is correct. You actually recover the detailed spatial temporal distribution for the Kuramoto-Sivacinski. You recover it in more details also in the phase space. And the thing that is even more surprising to me, we can do predictions of turbulent channel flows at much less cost than a large eddy simulation will do. And I'm showing you here statistics like wall normal fluctuations, span-wise fluctuations, and stream-wise fluctuations that were not possible previously by doing the LED that I have down there. So there is excitement about this generative AI, at least in our lab, and I think there's a lot of interesting things to understand of why this thing helps the things work. Now, people talk about fluids and predictions, etc., and I would like to put down these 3 things that I would like to show you. In my PhD, I did simply the impulsively started flow of a Reynolds number of 10,000, and this is about 35 years ago or so. No, 35, 32. And now I want to show you that after 32 years, from 10,000, we have moved to 25,000, 50,000, and 100,000. And this is actually the amount of money that I will bet that in my lifetime, no machine learning algorithm will ever be able to produce this simulation. So I'm here, and whoever wants to make the bet, you can pay my kids, of course, if you lose. But anyway, so here's what it looks like. And this is actually one of the highest resolution simulations ever made, because it's using wavelet-adapted grids, and it's using about 500 billion points in 2D, so you can imagine what it would require in 3D. But you can see some incredible physics, and the question, of course, is, do you care about this physics? That is another question. But if we go about knowledge, and we want to see the picture of turbulence in 2D, past the bluff body, that's where you see it in front of you, and it takes people who know to program and to do numerics and to write great code, and so this is the thing that I have up there. There is one more message, I think Michael mentioned it, about pins and the like methods. And I would like to show you a very simple idea of how you can compare pins and understand what is good and what is bad about them. Basically, what you do with pins is you have an equation and you use a Galerkin representation using a neural net. Those of you who have taken hyperbolic equations, you will realize what's the problem with that, because you see that you gather information that is from all over the place and not only along the characteristics. So you're violating this, and that is an issue. So you could do something else. You can take any numerical method that you can imagine to solve the wave equation, and instead of solving it forward, you just put it in a square and you minimize it. So it should take you no effort to take any discretization, and instead of doing the forward, 3 diagonal matrices, etc., write it as a minimizer and give it to your particular optimization solver. Same as the pins. You can add penalties, except that with pins you can put penalties anywhere. Here you have to put them on the grid. But nevertheless, if I interpolate, I can also get them anywhere. So you can start to see here the difference between the 2 methods. And let's look at a case where pins actually work. I chose a particular case. You can see how the 2 methods give you very similar results. But now the big news is If we look at the convergence of the method, first of all, with pins, it's very difficult to do Newton method because of the size of the neural nets. With Odile, as we call it, you can do Newton. First of all, the black points there, they show you different initializations for the neural net. You don't always get the same answer, but this doesn't matter. More or less, you get this thing to converge. But of course, you have to understand, because you are local and sparse, you can be much, much faster. So here's a method that can do anything that pins do, and it's 100,000 times faster. And I challenge you to download the codes, check it for yourself, put your favorite thing, and write back to us if you find different results. You can do also the thing of checking higher Reynolds numbers, and you find that things like pins don't always work. As soon as the thing becomes more hyperbolic, this pathology starts to appear, and so this is some of the issues that we encountered. So I'd like to close by my favorite type of algorithms, which is algorithms that are actually learning themselves. They're learning to solve problems, and we have a long heritage that goes from genetic algorithms and genetic programming. There is another class of algorithms that are called reinforcement learning, where the idea is that you are interacting with the environment, you take actions, and inside the brain here, you have some kind of a neural net. You have a model of the world, if you like. Here, the model is a neural net. That tells you what is the mean and the covariance of a Gaussian, that when you sample, you can take an action, and then you can calculate the cumulative reward. There is another way to look at these world models. I use a cartoon from Jürgen Schmidhuber. This is basically what we often do when we go about doing business, and you can encode it into the mapping of the reinforcement learning. In many, many things we do actually are reinforcement learning ideas. Someone discussed whether algorithms can discover something new. I have spent a lot of time studying fluid mechanics, and I was interested in the question, if I have two swimmers, how should they swim in order that the second swimmer can swim more efficiently than the swimmer in front? I was not able to find a control algorithm or anything like that that would solve this problem. So here is the solution through reinforcement learning. That's actually the early stages of learning, where you have a swimmer down here that does what it wants, and then there is another one who receives some information about the environment, and then this swimmer, which is on the top, is learning, and it's actually doing something very interesting. It goes like a missile into the wake of the other swimmer. It does not bypass it, it turns around, and it starts surfing the vortices and the fluid mechanics that are coming out of that after you see it, after you discover it through an automated process, are just absolutely spectacular. Eventually, at the later stages of learning, this thing finds a particular arrangement, and you have to observe how vortices turn and how the head turns. And this thing is producing you a 28% gain in average efficiency. You can extend it, and you can generate or extract energy in 3 dimensions, and so on and so forth. So control problems through reinforcement learning, once you phrase them in the right way with states, actions, etc., are very, very interesting problems, and I find the language of reinforcement learning very, very powerful. I'd like to show you one last innovation about reinforcement learning, which I think we are probably among the few that are doing this in our lab. So this idea is to use reinforcement learning to solve equations. And I will talk actually about using reinforcement learning to solve under-resolved equations. The idea is that you have a grid, and you use a grid to solve an equation. And when you use the grid to solve an equation, you come up with a numerical method that tells you how to evolve the solution over time. So now what you can do is you can introduce inside this grid agents, and now these agents are learning, and they complement the numerical solution. These agents can learn to capture global quantities like the energy spectrum. They can capture other constraints that you want. So we have, I believe Professor Hiro mentioned it, we have computational elements and learning agents working together. And in fact, because you are doing under-resolved simulations, the learning agents are correcting the implicit numerical error of the grid. So here's an automated process of solving under-resolved equations. We studied homogeneous turbulence as a three-dimensional problem, as a nominal problem. We wanted to see if we can outperform the classical Smagorinsky model. The results speak for themselves. You can see that we train on these Reynolds numbers, and then we can actually interpolate and extrapolate to larger Reynolds numbers, outperforming both the dynamic and the standard Smagorinsky model. We repeated this exercise for wall models of LES. Here, we train the channel flow up to less than RE tau 10 to the 4, and with a certain 5% accuracy, we're able to predict the friction drag up to Reynolds number tau 10 to the 6, which starts to be airplane level of Reynolds numbers. And a generalization is you study channel flow, and you can actually, with the same code, do turbulent boundary layer. I'd like to close, and I'd like to close by, again, going between the good and the bad, if you like. So we said that machine learning is perfect at image recognition. I don't know how many of you know this paper about the elephant in the room. You take a machine learning that has learned to detect all the objects in a room, and then randomly you take a little two-dimensional elephant and you plug it in there. And when you plug it in the image and you give it to the neural net freaks out, and sometimes it mixes a sofa for a person, and so on and so forth. So if neural nets have been trained on data that complete all the knowledge that we have, they're extremely powerful. In case there's weird things like an elephant in the room, then there is a problem. There is also the issue that has been raised by people that whether the things that you produce are necessarily should be produced just because we can. If we can make something, should we? And then there is this issue about this noisy parrots. There is a paper there that talks ChatGPT as a noisy parrot. So then I asked ChatGPT to give me an image of the paper on the dangers of stochastic parrots. And ChatGPT not only gave me a beautiful image, he also tries to convince me that this is actually a really good thing, where the vast scale influence of large language models as it offers is a landscape of intellectual debate and ethical considerations. So there is concerns. There is people, this New York Times on Sunday were talking about AI-generated garbage is polluting our culture. So there is some AI-generated garbage polluting also science. At the same time, I'll show you a moment of surprise that I had. I just wanted to say to ChatGPT, okay, let's see how stupid you are. And then I said, can you compare for me multigrid and UNets? And if you think about that, both of them are multi-scale algorithms, and they have similar structure. The answer is better than what I would have ever thought I could give myself. So I was taken aback about that this is kind of a friend that you can talk to, and you can get ideas, and then you can interrogate whether such ideas are interesting. So closing, I believe what I said in the panel. There is a review article, a mini commentary article that I write about scientific computing and AI, and there is plenty of room in the middle. I distinguish as the features of the two different domains, the ones that I am listing here, and I think it's important when we create algorithmic alloys where you try to put these two things together to develop exciting new frontiers. So I believe algorithms is here for us to stay. Computers are here for us to stay. At the same time, we should remain philosophical. So for the future, I believe that this is something that we may want to encounter. And with that, I would like to thank you and take any questions that you may have.
Thank you very much for that talk. Any questions from the audience?
So much for the very fantastic and also insightful talk. I have a very specific question about the research work you mentioned with the generative AI for the simulation. So you mentioned about the conditional diffusion, right? Have some like latent variable. So I'm wondering, like from your perspective, what kind of this kind of the latent variable or the controller is in this kind of the scientific simulation, and also what kind of distributions you think that is captured by learning this kind of diffusion model? Is that from the spatial or temporal dynamics given the data that is trained on, or is there any boundary, right? Because there are so many different examples, we cannot train on all the data. So what kind of the distribution you think it captured compared to the real scientific or the physical world distribution it should be?
I very much appreciate the question. I had all these questions myself when my postdocs presented me with this. So this is turbulent channel flow. The geometry is two flat walls. Okay, there is walls happening there. And so what this thing has learned, I think it has learned, so what we do, the downsampling, is simply a filtering of the microscale field, of the LES, high resolution LES of high resolution DNS. So we just do a filtering. The reason we do a filtering and we don't do an autoencoder, because if we had an autoencoder, we could do also filtering with an autoencoder, but we will not be using the decoder, because for the decoder, in our case, we're using the diffusion that we have learned. So in our case, the results I showed you is very actually simple downsampling of the data, and then we are learning. We're running the diffusion model using us on the microscale data over a lot of flow-through times of the flow. So it has captured, I believe, the statistics of the turbulent flow, but using as guidance the latent space dynamics of the filtering that we did. So I was surprised myself that something simple like that seems to be doing well. But I think, on the other hand, if you consider that it has been trained in all these statistics, and the statistics somehow have been captured. So it's no surprise that later when you evolve this flow is in a statistical equilibrium also. So when you are evolving the flow and you're evolving the latent space dynamics, in a sense, it memorizes things that it has found from before. But nevertheless, with neural nets and turbulence and so on, I have never seen anything so dramatic as capturing details in the way that this thing does. I was convinced that this is dead, and I was all in reinforcement learning, but this generative AI is a new dimension, which tells you why I'm enthusiastic about all these new ideas. So.
I have a more general question. So how could you tell that your model is actually learning the physics other than just picking up some pattern in your data set and then try to reproduce that pattern?
I don't, and the general answer is I don't. But now if you want to specify to the examples that I showed you, in the case of the reinforcement learning, there is a clear answer there. There is a reward. There is a reward that this thing is swimming. I can compute the drag, and I can compute the pressure, and I compute the swimming efficiency of the animal behind, so I know that the drag has gone down. And then that's actually something that philosophically is very important. Sometimes it's more interesting to study the physics of the control flow than the physics of the uncontrolled flow. Because then when I studied the physics of the control flow, what I found, it made sense. What this thing does is it receives vortices, and then it generates a dipole that it sets a dipole into the wake. And if you look at the formula of the drag coefficient, if you're able to have a body that generates dipoles into the wake, this will have always less drag than something that has one-side vortices. So the physics I learned after I analyzed the result. There was no physics infused inside my reinforcement learning. So I don't know if this answers your question, or if I have left something open.
But like, how could you tell that? Could you tell then in this way that your model is picking up the physics of the flow, like the
flow? It has figured out. Don't forget, the simulations here are DNS. The flow is resolved. What the learning here is the animal has learned how to swim to use the vortices. And this was done by reinforcement learning. It's discovery of reinforcement learning. It's not as fancy as doing AlphaGo or AlphaFold, but reinforcement learning has figured out a swimming pattern that at least myself, I would have never thought imaginable. The physics do make sense. After you analyze what it has done, it's beautiful what it has done, but I would have never thought about it.
Thank you.
Welcome.
The break is coming up. After the break, we'll have a discussion on building an ecosystem around SciFM moving forward. But before the break, let's please thank Professor Koumoutsakos one more time.